In November of 2015, at a conference for closure developers, Matt Adderith gave a presentation on the Dactyl keyboard. In the presentation linked below, Matt outlines how he went about creating the Dactyl keyboard, which is, quote, a parameterized, split-hand, concave, columnar, ergonomic keyboard. Inspired by the ergonomics of the Kinesis Advantage keyboard, Matt used Clojure to generate commands in the somewhat cumbersome OpenSCAD syntax to generate the 3D models for the right and left enclosures of the keyboard. With these models generated, the keyboard enclosures can be then 3D printed, which will accommodate the key switches and other electronics required to produce a DIY ergonomic keyboard. As a self-professed fanboy of the Kinesis Advantage myself, both Matt and I have stated,
I use one of these, it saved my hands.
I've been using the Advantage 2 for about a year now, and I find myself lugging it between school and work on a regular basis. And with the vid in full swing at the time of this video, I had some hobby time burning a hole in my pocket. Since the 2015 debut of the Dactyl keyboard, many forks of Matt's original repository have been made. The Dactyl Manuform is a twist on the original Dactyl keyboard. This changes the arrangement of the original thumb clusters in order to lower the overall height. There was a fork of this which allowed for the ability to accommodate different types of key switches, but with a modified thumb cluster with only 5 buttons, a Kinesis fanboy like me needs 6. After some searching, I arrived at a fork created by a GitHub user called CarbonFet, who kept the 6-button thumb cluster and made other parameterized improvements that I was looking for. So I forked this repository and got to work. Alright, time to start gathering some components. I went with parts from Amazon for my build, but you can get many of these components at a fraction of the price shown on screen from AliExpress. I'm an impatient guy and I paid a premium for Amazon stock instead of waiting 1 to 2 months for them to ship. So to get the keyboard to actually keyboard, we'll need some microcontrollers. Both the left and right hand sides of our keyboards are going to use an Arduino Pro Micro to detect keystrokes and send data to the host machine. We're going to be using QMK Toolbox to flash these guys, saving us the huge hassle of writing the keyboard driver from scratch. More on that later. The two halves of the keyboard will communicate to one another using a 3.5mm cable. Just make sure it has at least 3 conductors in it. For this connection, we'll also need to solder 2 jacks to the Pro Micros. The PJ325 form factor shown here is compatible with the controller insert found on my GitHub. For the key switches, I went with Otemu Browns. I'm used to the Cherry MX Browns in the Kinesis, so I figured that I'd go with these guys. 4 packs of 20 gives me enough for the keyboard I'm looking to build. We'll need plenty of 1N4148 diodes to wire up the key matrix, 74 of them to be exact. I went with this pack of 100. I bought a set of keycaps. These guys seemed cheap enough, but these weren't enough to handle the extra 10 1.5 spaced keys that I needed. These are the same size as a standard tab key, so I went with these guys from Pimp My Keyboard, and I picked up some purple singletons while I was at it. The rest of the components were things that I already had on hand. This includes some ribbon cable and some Cat5e cable that I had lying around. Having some solid core wire on hand is going to be useful for wiring up that key matrix. You're going to need a pair of side cutters and some wire strippers. Some stranded wire is nice to have, and a set of helping hands will help maintain your sanity while soldering, for which we'll need a soldering iron and some rosin core solder, which should round out the electrical side of things. I used my trusty CR10 and some black PLA filament to print the parts. And I made the decision to paint the enclosure, so for that I used some sandpaper to prep the surface, some spray primer to help everything stick, cheap acrylic craft paint and brushes got me through the painting process, and I topped it all off with some spray gloss. So now we have our parts together, time for us to generate some 3D models. So if we want to start making customized keyboards, we need to set up a few different tools first. The first one is Lineagen. Its job is to manage our actual Clojure project. The Clojure runtime will execute our Clojure code, which we can tweak to produce different keyboard styles. The Clojure code spits out the commands that OpenSCAD is going to need in order to generate the 3D models for our keyboard, and it can output these models as standard STL files. And once we have those, we can use some slicing software to take those STL files and then turn them into G-code, which our 3D printer needs to actually print the parts. I'm going with Prusa slicer, but you can use whatever slicer you want for this. If you're simply interested in using the STL files that I used in this build, you can just grab them from my GitHub repo, including the custom microcontroller insert that I made. If you aren't interested in seeing how to set up Lineagen, Clojure, and OpenSCAD in Linux, feel free to skip ahead to the timestamp on screen. But for the rest of you, here's how to get set up. So I'm setting up the tools in Arch Linux, but the instructions are pretty much the same for any distro that you might be on. First, we'll go to my GitHub, link is in the description, click clone or download, and copy that to your clipboard, bring up a terminal, and here's my home directory. I'm just going to make a temporary directory for now, and we'll go into there and then type git clone and then paste that link in. That'll download all the files from GitHub, and then when that's done, we can navigate to the source directory inside of there, and inside of there where there's another directory which contains our dactyl.clj file. So open that up in Vim. So this is the actual file you can modify to change different parameters. So I've gone with a 5x7 layout with these different parameters set, so you can tweak this to your liking. I've modified the script to only produce left and right models for the keyboard, and that will spit them out as left and right.scad in the things folder. That's how the actual script works, but we need to set up our development environment first. So we'll set up our tools here. Start with Lineagen, go to lineagen.org. Here's the instructions here. So it tells us to download a lean script, or line script, I guess. We'll copy that link here. Let's go back to our home directory here. We'll make a directory called bin, and we'll change a directory into there. Now type curl-O and paste that link in, and that will download the line script. We need to make it executable, so chmod all users plus x, and then the path to the script, and then just run the script by typing line. And there, Lineagen's installed. So now we can go to set up Clojure, so go to clojure.org, get started, and then we'll follow the install instructions for Linux, and we're downloading another script here with this command. So copy that command, you just paste that in, and that'll download the linux-install etc. script. Make that executable, chmod plus x, and then the path to that script. And then we'll run that script by typing sudo // and then the name of the script. And type in our password. And here we go. So now Clojure is all set up. So now what we can do is we'll go set up OpenSCAD. Now I'm on Arch, so depending on your distro, this is where it might vary. So it's available on Pacman, so type sudo pacman-S OpenSCAD, yes, and then we'll test it out. Alright, it's working, done. So let's go back into the GitHub folder. This is the main directory, so you type line generate and it will generate the OpenSCAD models in a folder called things. So when that's done, we'll navigate to the things folder, and we can see we got the left and right .scad files inside here. So we can open up, let's say, the left one in OpenSCAD, and this is what it'll look like. So you can scroll out. There's our model there. So in order to get this out as an STL file into Prusa, so we'll need to click render, which I think is F6, and when that's done, ding, we'll go to File, Export as STL. I'm just going to save this to my desktop as left, and then we can open that up. So here is Prusa Slicer, so we can slice this model. Now here's the problem I ran into. The bottom of the model has some geometry it thinks it needs to support. So to fix that, I just went to the cut tool, set the Z height to 1 millimeter, and keep the top half. And then I'm just going to save the board as an STL file here. So I saved this to my desktop as left-fix.stl. Now the actual files on my GitHub are the fixed versions. And at 0.1 millimeter layer height, it looks like it's only going to take...
Many hours later.
2 days of printing and some cleanup later, this is what I've got. Now it looks a little plain, so let's slap some paint on it.
Hello and welcome to the Craftman Show. My name is your host, the Craftman. In today's video, we're going to talk about hydro dipping. How that you can dip some things into hydro and make some exciting and new vigorous creations.
To get this thing wired up, I hopped over to the QMK firmware repo. The wiring diagram found there shows how to wire up the two Pro Micros to our TTRS jacks. The jacks need to be wired to ground, VCC, and pin 3 on each micro. Then I checked out the 5x7 folder and looked at the config.h header file. We can see which pins are used for both the row and columns for our key matrix by looking at the hash defines. I use this pinout diagram linked in the description to determine which pins need to be connected. The diode direction is also indicated as column to row, which means that the diodes need to allow current to flow from the column pins to the row pins. The last file of interest was 5x7.h, which indicates the specific rows and columns each key switch needs to connect to. I made a reference image and full schematic, which can be found on my GitHub repo. Now let's cue the soldering montage. To get this thing programmed, I'm using the QMK configurator tool. And for my keyboard, I'll go with the hand-wired /Dactyl Manuform /5x7 as my keyboard. The default layout is what I use to make my schematic, so I actually don't have to change this around whatsoever. So I'm gonna name my key map CMD Dactyl Manuform, and you can change the appearance of the on-screen display via a drop-down menu here. I just went with Space Cadet because it's easier to read. Now, there's a default key map that you can go with here just to test things out, but I'm gonna take the time to tweak it to something more akin to the Kinesis layout that I'm used to. Now that I've got a key map that I'm happy with, I can then compile it. So we click compile and wait for our cosmic potato to finish baking. And once that is complete, we then have the option to download both the full source code and the firmware. I'd suggest downloading the full source code in order to obtain a file called keymap.json. So this file you can then actually upload to the reconfigurator tool without having to do that programming thing all over again, as far as the key map's concerned. The file that we need to flash our actual microcontrollers is the .hex file. So you can get this by clicking the download firmware button, and then just save that somewhere where you can get it later. And you're also going to need to install QMK Toolbox. So once that's installed, you can open it up. Then go locate your .hex file, and then click flash. So if this happens to you, like it did me, what you need to do is just hit the ground and reset lines together, just short them out with a piece of copper. The problem is that Windows is trying to install the Arduino drivers before you have a chance to flash it. So what I did is just do it again. Be quick on the draw, hit flash, and then we can get our boards actually programmed. So now you can bring up the QMK configurator tool and just test out your key map. So far so good. Looks like all the buttons that I'm looking to use are programmed. So here's a typing demo.